All right, this is homework 2, question 5. So here we have a circuit that's full of capacitors. We're told that the capacitance of C1 is 2 microfarad, C2 is equal to 4 microfarad, and C3 is equal to 3 microfarad. Okay, and with these large circuit problems, well, let me first say this. Whenever you see something like this, where there's this gap right here, you can imagine there's a battery. There's always a battery. So we established where our battery is, and with these larger circuit diagrams, it's always easier to start furthest away from the battery and work in. So what does that mean? Like, here's our battery, think furthest away, so that's somewhere in this realm, right? And then you work in. Working from the furthest position, we'll see we have these 3 capacitors right here. Between them, there is not a single junction, therefore they're in series. So what do we do with capacitors in series? We just do that inverse addition, right? So I'm going to say 1 over CS is equal to 1 over 2 plus 1 over 3 plus 1 over 4. You're going to clean all that up, and what you get is CS is going to be equal to 0.92 microfarad. Okay, so the tedious part of this is then you have to redraw. So let's redraw real quick. Do something like this. Sorry, this takes me a sec to redraw. Okay, and what I like to do after this is I always write it in quotes. I'm going to write CS in quotes. And the reason I write it in quotes is like it's imaginary, right? Effectively, we have these 3 capacitors condensed into this quote CS capacitor, right? It's like an imaginary one. It's made up of 3. So that reminds me that like this was born from these 3. So let me just label my other ones down here. Okay, again, I like to think work furthest away from the battery and work in. If I look closely here, I can see that my current, comes off the battery like this, works all the way along, junction here and junction here. So I made the point, there's a junction here and here. But let's just talk about this position for now. How do I know it's a junction? Well, that's because the current here moving along this way has a choice. It can either go this way or it can go this way. Any point where the current has a multiple like routes of that it could go, we consider that a junction. I like to denote my junctions with like a dot like this, different color. I'll call it C and D like they do. And because we have 2 circuit elements separated by a junction, we can call them in parallel. And from now on, whenever you see me circle circuit elements like this, like a soft thing, see how it's like curved or going around like that, that means in series, and a box is in parallel. So that's just some notation. So what do we do with these capacitors in parallel? We just have to add them, right? So I'm going to say CP, that's for capacitors in parallel. That's equal to C2 plus, remember, it's that quote CS. And then CP, it equals to 4.92. Okay, so now we get to do the fun part again, which is redraw. Just to save the time, I'm going to duplicate it using like the iPad. Okay, so now this is made up of both C2 and that CS. So effectively, it's that quote CP. So that's just how I like to do it. Again, working furthest away from that battery, I can see that I have these 3 guys, and these are no longer junctions here, actually. And I can circle them and say that they're in series. What do we do with these circuit elements in series? Well, capacitors in series. In fact, with resistors, as we'll soon see, we do the opposite. But for now, let's worry about the capacitors. All we do is add them. So then 1 over CS is equal to 1 over 3 plus 1 over 4.92 plus 1 over 2. Work all that out, and you'll get 0.97 microfarad. And this was like, I did this very quickly. So the rounding might be off, but it is more or less along these lines. Let's recondense again. So it looks something like this. I'll redraw actually. and this is our effective CS. And by now you should notice that there's a little bit of a pattern going here. Again, we have a junction, right? Current can go this way, current can go this way. So what are these two? They are in parallel. What do we do with capacitors in parallel? Just add. So that will be CP is equal to C2 plus CS. Like this. What's that addition equal to? All right, it's somewhere here, 4.97. Actually, I wrote it as 4.65. So just so I don't continually write it wrong, or later write it wrong, I'm just going to write what I originally wrote. Okay, now we can compress these guys again. And what we'll have is this. And this is that new CP. And at this point, it should be very clear that these guys are in series. We just do that inverse addition. And at this point, we're solving for CEQ. So what's that CEQ equal to? That's 1 over 3 plus 1 over 4.965 plus 1 over 2. The equivalent capacitance is equal to 0.97 microfarad. Okay, so that's the answer to part A. 0.97 microfarad. And I'll pause the recording and take questions. So now in part B, we're asked to determine the charge on the capacitors that are closest to points A and B when the potential difference between A and B is 200 volts. So effectively, what we're told here is this is a 200 volt battery. And we're looking for the charge. We're looking for Q at this position. Let's call this Q3. We're looking for Q at this position. Let's call this Q2. And we're looking at Q1. Okay. Now, if you have a good eye, you'll see that what we just drew, right, where the battery is basically right here, 200 volts. So charge for Q3, that's right here. For Q2, I'm sorry, for Q1, that's right here. However, we can't solve for Q2 yet. Q2 is up here, right? This capacitor right here, we're at CP that's in quotes. It's in quotes, right? It doesn't actually exist. So we have to work a step back. And we'll get to that in a sec. But for now, let's solve for Q3 and Q1. So one of the properties of these capacitors is any capacitor that is in series. So right here, we're all in series right here. Any capacitor that is in series has the same charge. So we can solve for QEQ, which is equal to CEQ times V, right? So that's the equivalent capacitance, 0.97, times the total voltage, that's that 200, is equal to QEQ. And QEQ is equal to 194 microcoulomb. Okay? So therefore, we can say QEQ is equal to Q3, which is equal to Q1, which is equal to 194 microcoulombs. Wow, that was not right. Like that. Perfect. So go back here. Let's hit this with the check marks. We got this one. We got this one. And again, that's because these two right here are truly the capacitors that are right here. And when we solve for CEQ, that makes up for the charge that is felt by all of these, because again, they're in series. But what about this guy right here? We can't use this capacitor to solve for it. Rather, we need to work a step backwards and we can solve for this one. So how do we do that? Well, we need to first find the voltage drop that is through this capacitor. So how do we solve for that? Well, we know what the charge at this capacitor is, right? Again, it's in series with all of these guys. So it's equal to QEQ. So we can say, here, let me just label so I can kind of show you how I'm stepwise thinking about this. That was step one. In step two, we need to solve for that voltage. I think somebody in the waiting room, one second. Okay, so we need to solve for that voltage. So we know what the charge is there. The capacitance there is going to be that CP in quotes. So CP in quotes. And you know what I'll do? I'll say CP and I'll put like a alpha there. So we remember it's coming from there. That's that alpha, right? And then times V. What we're looking for is V, so we need to rearrange this so we can say QEQ over the CP alpha is equal to V. You plug in, you know, what CP alpha was, which was this guy right here. So that 4.965, and then QEQ we have, you solve for V. V comes out to be equal to 39 volts. Okay, so here we have established the voltage drop, 39 volts. 39 volts. Let me make it purple. I'm sorry, orange, so it's different color. 39 volts. And by definition, any capacitors that are in parallel share the same voltage drop. So we can say right here, this is equal to 39 volts, and this one right here is equal to 39 volts. Now, we have enough to solve for Q2 because we know what the voltage is. We know what C2, the capacitance, is. So we can use our equation, C times V is equal to Q. So part 3 of what we just done, we'll say this. Q2 is equal to C2 times V, where C2 is equal to 4 times 39, which is equal to 156 microcoulomb. Q2 is equal to 156 microcoulomb. And just for like sake of it coming up in the future, if you ever want to check to make sure like your answers are right, you're on the right path or whatever, the entire voltage drop of a system, even if it's made up of a capacitor in quotes, will equal 200, right? So if you solve, we solved it last night, but if you solve for the voltage drop right here and the voltage drop right here, sum them all, right? So here it's equal to 39. You add it to whatever this one is, add it to whatever this one is, it'll equal 200. So that's a little way you can check if you're ever curious. And the same thing can be said here. All the voltage drops here would be equal to 200, and so on as far as you go back. But it obviously is fastest to do it when it's has less elements there. Okay, so pause the recording and questions.
Yeah, I've got a question.
So looking at part C here, we're going to determine the potential difference between points C and D. Okay. So how am I looking at that? Well, we know that we're going to have a final position minus an initial position, right? We don't know what it's equal to. And just to be clear, let's just label. So here's our final. This is our initial. Okay. So we have to look first for the last place C and D were made up, right? That would actually be right here. So this was D, C. Oh, wait, no, I have that. And we're gonna have arrow going that way. So from this D to C, that's going to be equal to the charge of this position right here. Let's call that Q double prime, divided by the capacitance at that area. So that would be equal to that 4.96. Right? And what's that Q double prime? Well, Q double prime is equal to the that capacitance there. So that's CS being right there. So it's 0.965 times the voltage at this position. And remember, we already solved for voltage drop here. That's equal to that 39. So just multiply by 39. You solve for Q double prime. And this is equal to, this is what we were just talking about, that 37.7. And you divide that 37.7 times that 4.965. And what you get is something like 7.6 volts. Okay. Oh, wait. This should have been the 9 too. I wrote, sorry, when I solved this wrong, I wrote the wrong location. All right, this needs to move up one. No, actually, that's right. That's right. Let me see. Let me just check the answer real quick. .6. Okay, yeah, this is good. This is good. Okay. Okay, so we brought up a good point. The reason why we're going to use that 4.92 is that's the last time we had this C and D, where between them was a capacitor that truly existed, not that one that was in quotes, right? So here, this one's in quotes, and here, this one's in quotes. So that's why we use that 4.92 to solve right here. So this is homework 2, question 6. A capacitor with capacitance 6 is connected to a 20-volt battery. After the capacitor is charged, the battery is disconnected. The capacitor is then connected in parallel with a second capacitor with capacitance equals to 8 microfarad. The second capacitor is initially uncharged. We want to determine the charge on each capacitor after they have been connected. Okay, so question number 6. With this one, let's write out what is known. So we don't know what the charge is on the first or second afterwards in either case, right? So that means like Q at capacitor 1 final is unknown, and Q2F is also unknown, right? And after a while, they're going to be at equilibrium. So let's just keep that in mind. We know what C1 is equal to, which is equal to 6 microfarad. We know what C2 is equal to, which is equal to 8 microfarad, and we know what the battery is. I'll just write it down. So the initial 20. Okay. So with these ones, it's nice to think, we're going to have some change in Q. So by definition, we're going to have a Q before, which is going to be equal to a Q after, right? There's going to be no added battery or anything, same battery. So before, what is Q equal to? Q is equal to CV. So before, it's equal to C1 V0. Afterwards, though, it's going to be equal to C1 VF plus C2 VF. What we can do here is factor out that VF, leaving C1 plus C2. And we're going to be able to isolate VF because that's what we're going to need to solve for. Such. Okay, so now plug everything in. So that's going to be 6 times 20 divided by 6 plus 8, which is equal to 8.6 volts. So therefore, VF is equal to 8.6 volts. Okay, perfect. So now we can solve for the charge after with respect to both capacitors by saying Q1 F, which is equal to, oh no, let me do this. Q1 after, after you connect it with the second capacitor is equal to the C1, so that's capacitor 1, times VF. Remember, Q is equal to VF, which is equal to, I didn't solve this part, so I'll leave that. If someone wants to solve it, just say it out loud and I'll add it. After, which is equal to that C2 times VF. And it's just that simple multiplication, right? We already know what C1 and 2 are, and VF we just solve for. It'll be like 50 and like something else pretty close to 50.
51.6.
51.6 microcoulomb, and what's the other one? Should be bigger.
68.8.
68.8. So thanks to whoever did that. But if you're doing it, just, I don't know, just double check if I'm just to be safe. I believe you, but just double check. Okay, pause. All right, so this is homework 2, question number 3. And here we have this triangle, right? We know what the length on each side is. It's equal to 1 meter. Maybe I have to be neat here, sorry, because it's going to have a lot written on it. 1 meter. And we want to, determine the electric potential at the midpoint of each side. Okay, so the electric potential, right? Or potential difference or voltage, whatever you want to call it. So we're first going to need to find the distances that everything is away from each other. So let's first solve for it at position number 1. Oh, so let's just call this one P1. Potential at 1, 2, down here. Okay, so everything's distance away. So from here to here, it's just equal to L over 2. And then from here to here, again, that's equal to L over 2. And then from here to here, well, we'll call that D. Okay, and how we're going to have to find this is going to be using some trig, right? So let's break this down like this. So we have a right triangle right here. We know that it's equilateral, so that means this is 60. By definition, this is 30. Okay. This whole one right here is 60. This is then, let's call it alpha. Wait, no. This is a right angle. Wouldn't this just be 30? Yeah, this is also 30. Right? Yeah, this is also 30. Sorry. This is 60. Okay. And let's call this Y. Right here, this is Y. And if we do okay, so let's call that Y. Let's call this X. Sorry, guys, give me one sec. Okay, and then we can solve for Y because we can say this. So this is A, or this is part 1 of how I'm doing this. We can solve for Y by doing L over 2 sine 60 is equal to Y. So let me grab my calculator. So that's 1/2 times 0.5 times sine 60 is equal to 0.43. So Y is equal to 0.43. Now we can solve for X using Pythag. So we'll say X is equal to the square root of L over 2 minus that Y value squared. Oh, this should be square 2. So that's okay. So that's equal to 0.25 meters. And now we can solve for this value. I feel like I might be going a long way, but that's okay. We'll call this L prime. And we can solve for L prime as L minus X is equal to L prime, right? So that's going to be equal to like 0.75. Okay, and now we have enough to solve for D. and solve for d because we know that y over sine alpha, which is that sine 60, is equal to d over sine 90. So d is just equal to y over sine 60. So that means d is equal to 0.43 divided by sine 30, 0.86. 0.86 meters. And now it's just the easy part of plugging everything in. So we'll say VP1 is equal to KQ1 over L over 2 plus KQ3 over L over 2 plus KQ2 over D. Factor out K. Q1 over 0.5. This is, L is equal to 1, so 1/2. Plus Q3. So that's Q3 over 0.5, and then plus Q2 over 0.86. And then I'll leave the fun of plugging in everything and multiplying to you guys. Okay, so again, this one, I guess the hard part is just working out the sides if you